Trigonometry. It involves things as simple as angles and sides of triangles to waves, which both can be applied to almost anything. Video game graphics, projectiles, trajectories, periodic motion, track celestial bodies, and much more. This is why understanding trigonometry is so important, as this concept is applied to countless fields in countless ways. Trigonometry was compiled by Hipparchus of Nicaea in around the 2nd century BC. He formalized its key concepts used by Babylonians and Egyptians, along with Ptolemy, who expanded Hipparchus's work. Soon, in Greece, they began formalizing this. India made significant advancements, Islamics refining theories for astronomy, and during the Renaissance, trigonometry made its way in Europe. In this video, we will cover the basics of trigonometry in right-angled triangles, and you shall carry out the trigonometric legacy. In right-angled triangles, there are several components or labels that you need to know. There is the right angle, 90 degrees, theta, the angle of interest, and the angle you're not interested in. Then, once you know where theta is, your interested angle involving in your problem, you figure out the types or names of the sides of the triangle. The hypotenuse is the side that is common throughout all right-angled triangles. It is the longest side, the slanted one. The side opposite to theta on the other side is the opposite. The last side next to theta is the adjacent, which means next to. Now, you can analyze the basic components. A tip to memorize the trigonometric functions is SOHCAHTOA. Why is it important? Well, first, the first letters correspond to the trigonometric function's first letter, and more importantly, look at the second and third letters. We have 3 letters for the 3 sides: O for opposite, H for hypotenuse, and A for adjacent. Take a look at how SOHCAHTOA links with the respective equations. For example, sine, so. Therefore, it is sine of theta equals to the opposite over hypotenuse. That's simple. How neat. Take some time to comprehend this information. Find the pattern. Alright, SOHCAHTOA. With this trick, you wouldn't need to memorize 3 whole equations. Just the 3 sounds. You can pronounce with ease. Well, cool. Let's look at some examples. Alright, we have this triangle here. In scenario 1, it is quite simple. We have a side and an angle. The first step, identify your components. In this case, we know the value of the hypotenuse and we want to find the opposite. O and H. SOHCAHTOA. It is so. S-O-H. Sine. Great. Now, we write the equation down. Sine of theta gives us O over H. We have the equation. Let's insert our values in. That gives us sin 30 degrees is equal to x over 5. Since we want to find x, we need to isolate it. By multiplying by 5, we get rid of the denominator, as dividing by 5 multiplied by 5 cancels each other out, leaving us just with x. On the other side, sin of 30 is multiplied by 5 as well. Hence, all we need to do is put that into a calculator, and there, we get the value 2.5. That's wonderful. However, what if it is the other way around? What if we have the numerator but not the denominator? In other words, the known sides swap with each other. Well, if we do the exact same process, just with a different known value, we get sine of 30 degrees is equal to 2.5 over x. How do we isolate x again? The same idea. We multiply by x to get rid of the denominator, and we get x times sine of 30 degrees equals to 2.5. I mean, it's still not isolated. To cancel x being multiplied with sine of 30 degrees, let's divide it by the same item to cancel it out. X is equal to 2.5 divided by sine of 30 degrees. Again, put that into a calculator, and we get the value 5. Hey, notice how that is the same value as we got in the other way? This proves that it works. As for the other functions, it is still the same procedure. Can you find the missing side on your own? Okay, here we have the same triangle, but this time we don't have the angle, theta. Only two sides. Apply the same steps. We are using the sine function. If we plug in the known values in, we get sine of theta gives you 2.5 over 5. You should know that 2.5 over 5 isn't sine of theta, so how do we isolate theta? Well, we can't just simply divide sin theta as the whole thing is a term itself, and dividing it doesn't give you anything. In order to find theta, you take the inverse function of itself on both sides. Instead of cancelling itself by dividing, as it doesn't work, we get its other opposite, you can say, which cancels out the sine of theta, equal to the inverse of sine of 2.5 over 5. Then into a calculator, we obtain the value 30, which is the same value as before. Another proof that it works. Can you find the missing angle on your own? What about this scalene triangle here, for example? We can't apply basic trigonometry to it. It only works for right-angle triangles. In this scenario, you can't apply basic trigonometry, but rather through some other means of doing so. Here are some examples for non-right-angle triangles. Pythagorean theorem. This famous and simple equation links the sides together, though it only works for right-angle triangles, but still very handy. Heron's formula links the sides with the area. Sine rule links each sides to angles ratios for each three. Cosine rule links an angle with two sides, relates with the Pythagorean theorem. When you have the chance, see if you could draw a line perpendicular to a base side through an angle. This would make things easier, as you would then have multiple right-angle triangles. Well, there you have it, basic trigonometry. At first, it might be a little challenging to adapt to, like the SOHCAHTOA trick. Procedures after identifying components, the components themselves, and more. For other functions, it is the same situations, scenarios 1 and 2. Remember, for scenario 2, when you are finding theta, that you are taking the inverse function, not dividing, which is what many people made this common mistake, and vice versa in scenario 1, where you have theta. To truly master this useful skill, memorize SOHCAHTOA and practice trigonometric functions and equations until you fly through them easily.